And welcome to Chapter 18, where we're going to be dealing with reaction rates and equilibrium. Throughout this chapter, we're going to be studying basically four major ideas. We're going to take a look at how reactions occur. Now, I use RxNS for my abbreviation for reactions. How reactions occur. And this is a topic that we're going to tackle using what's called collision theory. That's actually what we're going to tackle in this section of 18.1, collision theory. Then we're going to move on and try to talk about how far reactions proceed. Not all reactions go to completion. And so this topic of how far these reaction proceeds is dealing with an area called equilibrium. Equilibrium. We're going to be tackling that in 18.2 and 18.3. In 18.4, we're going to deal with the question of why reactions occur, RxNS, why reactions occur, and we're going to be talking about this in terms of energy, not philosophically, like why we're here. We want to talk about energetically what's making these reactions occur. That's a topic that we address using thermodynamics. And finally, we're going to wrap up Chapter 18, 18-5, talking about rate laws and mechanisms. We're going to come back to the idea of rates of reaction, but we're going to be using equations to define them, and that's a topic called kinetics. It also gives us an idea on how these reactions occur in terms of the steps that they take. So those are the four major topics that we're going to be covering in this chapter. So let's go ahead and jump in. Collision theory. 18-1 deals with rates of reactions. And so what we're going to try to do is figure out what affects how fast a reaction goes. Now before we do that, we want to go back and review what actually happens during a chemical reaction. I'm going to draw a line here across the top so we don't interfere with that. If you take a couple of reactants, let's say we have AB reacting with CD, what could happen is that AB could split, CD could split, and then the molecules could rearrange. But the very first thing that must happen during a reaction is that you must break the reactant bonds. So reactant bonds must break. And in order to break bonds, you have to put energy in. So energy is going in. Now when the molecules or the atoms rearrange themselves, and let's just say that A goes with D and C goes with B, all right, new product bonds are going to form. And when new bonds form, energy is released because they stabilize one another. So energy comes out. So energy always goes in to break the bonds of the reactants, and energy always comes out when you reform product bonds. All right? Now the question is, where does the energy come from to break these reactant bonds? Well, that's where collision theory comes in. Collision theory is going to tell you that the energy to break the reactant bonds comes from the collision of particles, or of reactant particles. All right, now we're not completing this story yet, but we will. Let's go ahead and scroll down here just for a second. So, therefore, if the energy to break reactant bonds comes from the collision of reactant particles, what factors will affect the rates of these reactions? Well, let's start with concentration. Okay? Let's say that you increase the concentration. Oops, these should be brackets, not an E there, just a bracket on one side, a bracket on the other. If you increase concentration, you should have more collisions. If you have more collisions, you should therefore have more reactions. If you have more reactions, it will occur at a faster rate. And if a reaction occurs at a faster rate, it takes less time for the reaction to occur. Now, on the other hand, what happens if we decrease concentration? Now, again, I use these brackets to denote concentration. If you lower the concentration, the opposite will occur. You will have fewer collisions. If you have fewer collisions, you'll have less reactions or fewer reactions. If you have fewer reactions occurring, you'll have a slower rate, and therefore reactions will take more time to go to completion. Now we're going to investigate this in class as we look at the iodine clock reaction. The iodine clock reaction is a fascinating reaction where the iodate ion reacts with metabisulfite and eventually will produce iodine. The iodine will be detected by a starch indicator and it will turn a jet black or kind of a very, very dark bluish purplish black solution basically in the blink of an eye. You can actually take a look at this online. If you take a look at the course website, we do have a video of this reaction. We will also be tackling this thing in class as well. So we should be able to predict in the iodine clock reaction what will happen to the rate if we go from 0.04 up to 0.07 molar solutions, or if we reduce the concentration down to 0.02 molar solutions, because concentration has a direct impact on the rates of reaction in many, many cases. All right? But as it turns out, not all collisions will result in a reaction. And in the next podcast, we're going to try to unpack why this is. We'll see you next time.